Imagine standing on the ground you're standing on right now. Except it isn't ground at all. It's an ocean of molten rock stretching to every horizon and glowing orange-red under a black starless sky. No oceans. No air you could breathe. No life anywhere in sight. Just fire and silence and time. That was Earth. Your Earth. 4 billion years ago. And somehow, through a chain of cosmic accidents so precise that even scientists call it improbable, that ball of boiling lava became the only place in the known universe where you and I could exist. Today I want to take you back to the very beginning, to the birth of our Sun, our Earth, and our Moon. Stay with me until the end, because the final piece of this story is the one event that made life on Earth possible at all, and it's honestly the most incredible part. Hey friends, welcome back to the channel. Before we dive in, if stories like this one that make you look at the world differently are your thing, do me a favor. Hit subscribe, drop a like on this video, and share it with someone who'd love it too. It genuinely helps this channel grow and it means a lot. Okay, let's go back. Way back. Chapter 1. The Cloud in the Dark. Rewind the clock 4.6 billion years. That's 4,600,000,000 years, and there is no sun. No Earth. No solar system at all. Just darkness. Deep, silent, empty space. But it wasn't completely empty. Floating quietly through that void was an enormous cloud of dust and gas made mostly of hydrogen and helium. Astronomers call it the Solar Nebula. In Hindi it's called Niharika. For millions of years it simply drifted undisturbed, going nowhere in particular. Then one day everything changed. Somewhere nearby, a dying star reached the end of its life and exploded in a supernova. Not the Big Bang. A supernova, the death cry of a massive star. And when its shockwaves slammed into our quiet little cloud, something remarkable happened. The cloud became unstable. Gravity took over. Pockets of gas and dust began to compress, and the entire nebula started collapsing in on itself, spinning faster and faster until it flattened into a rotating disk. What scientists call the protoplanetary disk. Proto meaning before. The disk that existed before there were any planets at all. Here's something beautiful. Because that disk was flat, everything born from it inherited that flatness, which is exactly why every planet in our solar system orbits the Sun on roughly the same plane today. You're looking at the fingerprint of that ancient spinning disk every time you look at a diagram of the solar system. At the center of that disk, pressure and temperature kept climbing and climbing until, at around 15 million degrees Celsius, something ignited. Hydrogen atoms began fusing into helium. A nuclear furnace switched on. Our Sun was born. That same fusion reaction is still happening right now, this very second, and it's the reason you're warm, the reason plants grow, the reason there's light outside your window. And it swallowed almost everything. Even today the Sun accounts for 99.8% of all the mass in our entire solar system. Which leaves just 0.2% left over. And from that tiny leftover fraction came 8 planets, hundreds of moons, thousands of comets, and millions of asteroids. Including us. Chapter 2. From dust to worlds. So how does 0.2% of leftover cosmic dust turn into planets? This is where it gets genuinely fascinating. In that spinning disk, tiny dust particles began bumping into each other and sticking together through static charge and weak chemical bonds, forming small clusters. Over millions of years those clusters kept colliding and growing until some of them stretched a few kilometers wide. These became known as planetesimals, miniature planets in the making. Once gravity pulled enough of them together to reach roughly the size of our Moon, they earned a new name, protoplanets. This entire process of dust becoming clusters clusters becoming planetesimals, and planetesimals becoming protoplanets is called accretion. A Soviet astronomer named Viktor Safronov first proposed this idea back in 1969. Nobody took him seriously at the time. It wasn't until 1984 that the scientific world finally caught up and recognized he'd been right all along. And we're not just taking his word for it anymore. Today, telescopes have watched this exact process happening in other solar systems being born right now light years away, dust particles clumping up to a centimeter in size within just a few thousand years. And here on Earth, meteorites give us physical proof. Inside many of them, scientists find tiny fragments called chondrules, leftover debris from before the planets even existed, containing radioactive elements like uranium and hafnium that let us date them precisely. Here's a fact that might blow your mind. The uranium found on Earth right now is estimated to be 6 billion years old, older than our entire solar system. It was forged inside a supernova before our sun was even born, and it's been sitting in the ground beneath your feet this whole time. Chapter 3. Welcome to Hell. Now picture those protoplanets, including the one that would become Earth, smashing into each other over and over across millions of years. These weren't gentle collisions. Each impact unleashed so much energy that it melted solid rock into oceans of lava. And with every collision, the growing Earth pulled in more mass and more gravity, slowly rounding itself into a sphere. Scientists have a name for this violent, chaotic era: the Hadean Eon, named after Hades, the Greek god of the underworld. Because that's exactly what early Earth looked like. Hell. This period stretched from 4.6 billion to 4 billion years ago, and during it objects as large as 100 to 200 kilometers across regularly slammed into our planet, melting everything they touched into fresh lava. But here's the twist nobody expects. This hellish violent period is the very reason we have water on Earth today. Many of the asteroids and comets crashing into our planet were carrying ice locked inside them since the formation of the original solar nebula. Every impact delivered a little more water. Some of it flashed instantly into steam and rose into the atmosphere, only to fall back down later as rain. Bit by bit, collision by collision, Earth was being seeded with the very substance that would one day make it livable. By the end of the Hadean Eon, our planet had become one uniform glowing ball of magma, held together purely by gravity. And that set the stage for the next transformation: differentiation. Chapter 4. Building the layers. Picture that molten Earth slowly sorting itself out like oil separating from water. Heavy elements like iron and nickel began sinking toward the center, pulled by gravity, denser than everything around them. Lighter elements like silicon, oxygen, aluminum, sodium, calcium, and potassium rose toward the surface. Over time, this sorting gave birth to Earth's core, mantle, and crust. At the very center, iron and nickel fused together into a core that today reaches temperatures of 6,000 degrees Celsius, hotter than the surface of the sun. Normally, iron would melt at that heat. But the pressure down there is so extreme that iron stays solid instead. That heat doesn't just come from pressure either. It's constantly topped up by the slow radioactive decay of uranium, thorium, and potassium sitting in the mantle above it. Speaking of the mantle, it's the thickest layer of our planet at more than 3,000 kilometers deep. Solid today, but back then it was a swirling sea of magma. As the lighter elements rose and cooled at the surface, they formed the crust, the thin outer shell we actually live on, made up of nearly half oxygen by mass. If you go deeper into the science, geologists will tell you Earth isn't really made of just 3 layers. It's 5. The lithosphere, the asthenosphere, the mesospheric mantle, the outer core, and the inner core. The lithosphere, the layer we live on, isn't even one continuous shell. It's broken into pieces called tectonic plates. Where those plates meet, you get volcanoes. Where they grind against each other, you get earthquakes. And in that swirling outer core, churning liquid iron generates electrical currents because iron conducts electricity, and those currents create something extraordinary, Earth's magnetic field. Without it, solar wind would have stripped our atmosphere away billions of years ago the way it did to Mars. This invisible shield is one of the biggest reasons life on Earth was ever possible at all. And interestingly, the solid inner core is still growing today, thickening by about 1 millimeter every single year as the liquid outer core slowly cools and crystallizes. Chapter 5. The collision that gave us the moon. Now here's the part 1 promised you, the one event that changed everything. For decades scientists debated where the moon came from. Maybe Earth's gravity simply captured a passing space rock, the capture theory. Maybe the moon formed alongside Earth from the very beginning, the co-formation theory. Maybe a piece of Earth just spun off on its own, the fission theory. All three were wrong. But one of them was closer to the truth than anyone realized. Around 4.5 billion years ago, while Earth was still a molten half-formed world, another protoplanet roughly the size of Mars was also taking shape nearby. Scientists later named it Theia. And about 100 million years after the solar system began, Theia collided with Earth. Both worlds were still balls of liquid rock at the time. When they collided, their cores fused into one, becoming part of the Earth we stand on today. But a massive chunk of debris was blasted outward in the impact, and that debris eventually coalesced into a new object orbiting our newly enlarged planet. That debris became the moon. We know this wasn't just theory because when NASA's Apollo missions brought lunar soil back to Earth, scientists found something striking. The basaltic rock from the moon's mantle and its oxygen isotopes closely matched rock found right here on Earth. The moon, quite literally, is made of us. And here's the detail that makes this collision matter so much. 30% of Earth's total mass comes from its iron-rich core. But the moon's core makes up barely 1.6 to 1.8% of its mass. Almost all the heavy metal from that ancient collision stayed here on Earth, while the moon was built from the lighter outer debris. That impact didn't just give us a nightlight in the sky. It knocked Earth's axis into a 23.5-degree tilt, the exact tilt that gives us seasons. Without it, our climate would have swung to such violent extremes that life might never have gotten a foothold. And without the moon's gravity pulling on our oceans, we'd have no tides, the very tides many scientists believe helped early life migrate from the sea onto land. In other words, without a catastrophic planet-shattering collision 4.5 billion years ago, none of us would be here having this conversation right now. Chapter 6. Building the sky, building the sea. As Earth calmed down from its violent youth, volcanoes kept erupting across the surface, filling the sky with water vapor, carbon dioxide, methane, and ammonia. A toxic mix almost completely lacking in oxygen. Not exactly a place you'd want to take a breath. But slowly, as the planet cooled, that water vapor began condensing and falling as rain for what may have been millions of years, carving out the first oceans. Combined with the water delivered earlier by all those icy asteroid impacts, Earth finally had liquid oceans covering its surface. And those oceans did something remarkable. They absorbed enormous amounts of carbon dioxide and heat, cooling the planet down to survivable temperatures and allowing oxygen levels to slowly rise. It's a job our oceans are still doing today. Most people assume forests absorb the majority of human carbon emissions, but it's actually our oceans doing the heavy lifting. And that capacity isn't infinite. It's a topic worth its own video if you're interested. Let me know in the comments. Closing. A planet that shouldn't exist when you step back and look at everything that had to happen. A supernova at exactly the right moment. A nebula collapsing into exactly the right shape. A sun settling at exactly the right distance. A planet growing to exactly the right size. A magnetic field of exactly the right strength. A greenhouse effect that was neither too strong like Venus nor too weak like Mars. and then on top of all of it one violent collision with a Mars-sized planet that just happened to tilt our axis and give us a moon, you start to realize something. None of this had to happen. And yet somehow it all did. That's the story of how a ball of boiling lava became the only home we've ever known, and honestly it makes you look at this planet a little differently, doesn't it? If this video made you see Earth in a new way, that's exactly why I make these. So please hit subscribe if you haven't already, drop a like on this video, and share it with someone who'd find this as fascinating as you just did. It helps this channel keep telling stories like this one. And if you want to keep going down this rabbit hole, I've made another video about what happened next. How life actually evolved on this planet and which animals we're most closely related to. Click here to watch it next. Thank you so much for watching, friends. I'll see you in the next one.